Algebra of Real Functions. Welcome, everyone. To begin our lesson on the algebra of real functions, let's take a moment to reflect on what we have already covered. In our previous sections, we focused on the fundamentals, learning how to properly define a function and how to identify various types of functions. Now that we have a solid foundation in understanding what a function is, we are ready to move forward. In this session, we are going to explore how to combine these individual functions using basic arithmetic operations. You might be wondering how this relates to what you already know. Well, think back to your work with basic arithmetic. Just as you can add, subtract, multiply, and divide real numbers, we can perform very similar operations on real functions. By the end of this lesson, you will see how these familiar rules apply to the world of functions. Functions definition. First, suppose we have two real functions. Let's call them f and g. We write this as f, mapping from x to the set of real numbers, and g, also mapping from x to the set of real numbers. Now, what exactly is this x? X represents the domain, and it is a subset of the set of real numbers, which we denote by the symbol r. The most important thing to notice here is that both functions, f and g, share this exact same domain, x. Because they share this common ground, we are able to combine them. This means we can define entirely new functions by performing arithmetic operations, like the addition and multiplication we are about to see in the next few slides, on their individual outputs for any given input x that belongs to our domain x. Now that we've introduced the topic of the algebra of real functions, let's look closer at what we need before we can actually start performing these operations. So, as we move forward into the specific operations, always keep this shared domain in mind. 1. Addition of functions. When we talk about the sum of two functions, f and g, we are actually creating an entirely new function, which we denote as f plus g essentially. The output of this new function is simply the sum of the individual outputs of f and g for any given input. To put this into a formal mathematical definition, we say that f plus g of x equals f of x plus g of x. If you are working through a problem, you can follow this simple three-step process. First, clearly identify the algebraic expressions for both f of x and g of x. Second, add those two expressions together. And third, simplify the resulting algebraic expression by combining any like terms. Let's look at a concrete example to see this in action. Suppose we have two functions where f of x equals x squared and g of x equals 2x plus 3. Our goal is to find the expression for f plus g of x following our steps. In step 1, we have identified our two parts. F of x is x squared and g of x is 2x plus 3. In step 2, we write out the addition, which gives us f plus g of x equals x squared plus the quantity 2x plus 3. Finally, in step 3, since there are no like terms to combine here, our simplified result is f plus g of x equals x squared plus 2x plus 3. Now that we understand that we can perform operations on functions as long as they share the same domain, let's dive into our first specific operation, the addition of functions. This same logic of combining expressions will apply to the subtraction and multiplication operations we will cover in the next few slides. 2. Subtraction of functions. Just like we did with addition, the difference between two functions, which we denote as f minus g, results in a brand new function. In this case, the rule is that we take the output of the second function, g, and subtract it from the output of the first function, f. To put this into a formal mathematical definition, we say that the function f minus g, evaluated at x, is equal to f of x minus g of x. To solve these problems accurately, I want you to follow this three-step process. First, clearly identify the expressions for both f of x and g of x. Second, subtract the expression of g of x from f of x. Now, I must give you a very important warning here. Be extremely careful to subtract the entire expression of g of x. I highly recommend you use parentheses around the second expression to avoid mistakes. Finally, simplify the resulting algebraic expression by combining like terms. Let's look at a concrete example to see this in action. Suppose we are given that f of x equals 5x plus 10 and g of x equals 2x minus 4. Our goal is to find the expression for f minus g of x. In step 1, we identify our two functions. F of x is 5x plus 10 and g of x is 2x minus 4. In step 2, we set up our subtraction. This is where that warning about parentheses comes in. We write the expression for f of x, then a minus sign, and then the entire expression for g of x inside parentheses. So it looks like open parenthesis 5x plus 10, close parenthesis, minus open parenthesis 2x minus 4, close parenthesis. In step 3, we simplify. When we distribute that negative sign into the second parenthesis, the minus 4 becomes a plus 4. This leaves us with 5x plus 10 minus 2x plus 4. When we combine our x terms, 5x minus 2x gives us 3x, and our constants, 10 plus 4, give us 14. So our final resulting function is 3x plus 14. Now that we have seen how to add functions, let's move on to our second operation, subtraction of functions. 3 multiplication by a scalar. Now that we have covered how to add and subtract functions, let's move on to our third operation, multiplication by a scalar. In this case, we aren't multiplying two different functions together like we will see in a later slide. Instead, we are taking a single real function, let's call it f, and a constant real number, which we refer to as alpha or a scalar. By using this scalar, we can create a brand new function simply by multiplying the output of our original function by alpha. To put this into a formal mathematical definition, the function alpha f of x is equal to alpha times f of x. If you are working through a problem, you can follow this simple 3-step process. First, clearly identify your constant, alpha, and your function, f of x. Second, multiply every single term within the function f of x by that constant alpha. Finally, simplify the resulting algebraic expression. To make this concept more concrete, let's look at a real-world analogy. Imagine that the function f of x represents the cost of just one single item. If you decide you want to purchase alpha number of those items, say 3 or 10, the total cost would simply be alpha multiplied by the function f of x. It's just scaling the original cost up or down. Let's look at a practical example to see this in action. Suppose our constant alpha is equal to 3 and our function f of x is equal to x squared minus 4x plus 2. Our goal is to find the expression for 3f of x. Following our steps. First, we identify that alpha is 3 and our function is x squared minus 4x plus 2. Second, we set up the multiplication by placing the 3 outside parentheses, so we have 3 times the quantity x squared minus 4x plus 2. Third, we distribute the 3 to every term inside. Multiplying 3 by x squared gives us 3x squared, 3 times negative 4x gives us negative 12x, and 3 times 2 gives us 6. So, our final simplified result is 3x squared minus 12x plus 6. 4. Multiplication of functions. When we talk about the product of two functions, f$ and g$, we denote this new resulting function as f$ times g$, written as fg$. Essentially, what we are doing here is taking the output of the first function and multiplying it by the output of the second function for every shared input. You might also hear mathematicians refer to this as pointwise multiplication, because we are multiplying the values at each specific point. To put this into a formal mathematical definition, the function fg of x$ is equal to f$ of x$ times g$ of x$. To solve these problems accurately, I recommend following this 3-step process. First, clearly identify the algebraic expressions for both f$ of x$ and g$ of x$. Second, write them down side by side in parentheses and multiply them. Finally, use the distributive property, which you might remember as the FOIL method, to expand the brackets and simplify your final expression. Let's look at a concrete example to see this in action. Suppose we are given two functions, f$ of x$ equals x$ minus 2 and g$ of x$ equals x$ plus 5. Our goal is to find the product, $fg of x. In step 1, we have identified our two expressions. $f of x is x minus 2, and $g of x is x plus 5. In step 2, we set up our multiplication. $fg of x equals the quantity x minus 2 multiplied by the quantity x plus 5. In step 3, we expand the expression using FOIL. We multiply x by x to get x squared, then x by 5 to get 5x, then negative 2 by x to get negative 2x, and finally, negative 2 by 5 to get negative 10. This gives us x squared plus 5x minus 2x minus 10. After combining the like terms, 5x and negative 2x, we arrive at our final simplified answer, x squared plus 3x minus 10. Now that we have covered how to add, subtract, and even multiply a function by a single constant, let's move on to our fourth operation, the multiplication of two different functions. Keep this expansion technique in mind, because in our next slide, we will look at the final operation, division, where we will need to be particularly careful about the values we are allowed to use. 5. Quotient of functions. Now that we have covered addition, subtraction, scalar multiplication, and multiplication, let's move on to our fifth and final operation, the quotient of functions. The quotient of two functions, f and g, results in a new function, which we denote as f over g conceptually. This is where we take the output of the first function, f, and divide it by the output of the second function, g. Looking at the mathematical definition, we write this as the quotient of f and g of x equals f of x divided by g of x. However, there is a very important condition we must always remember. This is only valid provided that g of x does not equal 0. As we will see in a moment, division by 0 is undefined, so we must be careful with our domain. To solve these problems, follow this step-by-step process. First, identify the algebraic expressions for both f of x and g of x. Second, place the expression for f of x in the numerator and the expression for g of x in the denominator. Third, and this is crucial, determine any values of x that would make the denominator, g of x, equal to 0. These specific values must be excluded from our domain. Finally, simplify the resulting fraction using your algebraic skills if possible. Let's look at a concrete example to put this into practice. Suppose we have f of x equals x squared minus 9 and g of x equals x minus 3. Our goal is to find the quotient, f over g of x. In step 1, we identify our two functions. F of x is x squared minus 9 and g of x is x minus 3. In step 2, we set up our fraction. F over g of x equals the quantity x squared minus 9 all over the quantity x minus 3. In step 3, we check our restriction. Since our denominator is x minus 3, we must ensure that x minus 3 does not equal 0. This means that x cannot be 3. We must note this restriction clearly. In step 4, we simplify. You might recognize the numerator as a difference of squares. We can factor x squared minus 9 into the quantity x minus 3 multiplied by the quantity x plus 3. This gives us a fraction where the quantity x minus 3 is in both the numerator and the denominator. We can cancel these terms out, leaving us with the simplified result, f over g of x equals x plus 3, with the essential condition that x is not equal to 3. Keep this restriction in mind, because in our next slide, we will summarize all these operations and discuss the important rules regarding their domains. Key takeaways. First, we need to talk about the domain requirement. When you are performing addition, subtraction, or multiplication, you can't just pick any number. The domain of your new, resulting function is the intersection of the domains of function f and function g in simpler terms. This means the new function only works for x values that are valid for both original functions at the same time. However, there is a special division constraint to keep in mind for the quotient function, f over g. Just like before, we start with the intersection of the domains of f and g, but we must add one extra rule. We have to exclude any x value that makes the denominator, function g of x, equal to 0. As we saw in our previous example with the fraction, we cannot allow division by 0. To help you study, let's quickly review this summary table of all the operations we've covered today. For addition, f plus g of x equals f of x plus g of x for subpara subtraction, f minus g of x equals f of x minus g of x for scalar multiplication, alpha times f of x equals alpha times f of x for multiplication, f times g of x equals f of x times g of x, and finally, for division, f over g of x equals f of x divided by g of x, provided g of x is not 0. Now that we have walked through each operation individually, let's bring everything together with some essential key takeaways. Keep these formulas and the rules for the domain in your notes, because in our next slide, we will look at some common pitfalls where students often lose marks. Common mistakes. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. As we've seen through our various examples of addition, subtraction, multiplication, and division, the algebra can get a bit tricky if we aren't being careful. Let's look at 3 specific mistakes that students often make. First, please be careful not to confuse multiplication with composition. It is a very common error to see the notation f times g of x and think it means the same thing as f of g of x. These are entirely different operations. Remember, f times g of x simply means you are multiplying the output of f by the output of g. However, f of g of x refers to function composition, which means you are actually plugging the entire function g into the function f. Always check your notation to ensure you know which operation you are performing. Second, when we are dealing with the quotient of functions, do not ignore the denominator. As we discussed in the slide on division, we must always state the condition that g of x does not equal 0. In mathematics, division by 0 is undefined. Therefore, when you are defining the domain for a quotient function, you must always exclude any values of x that would make the denominator 0. Finally, watch out for sign errors during subtraction. When you are calculating f minus g of x, a frequent mistake is forgetting to distribute the negative sign to every term within the second function. To avoid this, I highly recommend that you always use parentheses, writing it as f of x minus the quantity g of x. This ensures that the negative sign is applied correctly to the entire expression, preventing those small but costly algebraic errors. Keep these tips in mind, and you will find that mastering the algebra of real functions becomes much more manageable.